Do you see that? Of course not. Let's zoom in a bit. This right here is a quantum dot. You may have heard of it before, but what exactly is it? Quantum dots, or QDs for short, are tiny semiconductor nanoparticles with unique optical and electrical properties. The discovery of quantum dots is actually quite interesting. Quantum dots were originally discovered by two scientists at the same time in the early 1980s. Alexei Emkov and Louis E. Bruss were the first to study and observe them. First, Emkov, from the Soviet Union, was working with colored glass when he noticed something strange. The color of the glass changed depending on the size of the nanoparticles embedded inside of it. He realized this was due to quantum mechanic effects and identified these particles as quantum dots. Around the same time, Louis Bruss from Cleveland, Ohio, was researching semiconductor nanocrystals and made a similar discovery. He demonstrated that the size of a quantum dot directly influences the color of the light it emits. Because of this property, quantum dots have become valuable in a wide range of applications. For the sake of this video, we'll be focusing on the electrical applications. If you've ever been to a Best Buy or any electronics section in any store, then you've probably heard of QLED, meaning quantum dot light emitting diode. QLED TVs use quantum dot nanoparticles to enhance color accuracy and provide a more vivid screen. From display technology to quantum computing, the electrical applications of quantum dots are truly endless. But first, to truly understand how quantum dots work, we have to understand the structure of them. Quantum dots have a well-defined crystalline structure, usually taking one of two forms, cubic or hexagonal. This crystal arrangement plays a big role in their optical and electrical behavior. At their core, quantum dots are made from semiconductor materials like cadmium selenide, cadmium sulfide, and indium phosphate. The chemical makeup of quantum dots depends on its composition, but those common elements involved are chemidium, selenide, sulfur, indium phosphate, and zinc. These atoms arrange themselves in precise crystalline structures, either in their cubic or hexagonal form. Now, let's talk about bonding. Intramolecular forces hold the atoms inside the quantum dot's core together. These are covalent bonds between chemidium and selenium atoms, which form a strong, stable network that make up the crystalline lattice structure. To really illustrate this and show you what exactly I'm talking about, let's look at a physical model of a chemidium selenide quantum dot. So as you can see, this right here is a model of a chemidium selenide quantum dot, of course incredibly upscaled to size. The red styrofoam ball in the center represents the core of the quantum dot. The gray balls surrounding it represent chemidium atoms, each of which is bonded to 4 yellow balls, which represent selenium atoms. These covalent bonds, which are intramolecular forces, form the core lattice structure, and all of these atoms are arranged in tetrahedral arrangement. The structure altogether forms a cubic-like arrangement. You can also see pipe cleaners which extend outwards, representing ligands which interact with the surroundings via intermolecular forces, like London dispersion interactions. Intermolecular forces occur outside the quantum dot, particularly in how the ligands interact with the surrounding. These forces include London dispersion forces between the ligands and the environment, dipole-dipole interactions between the quantum dot surface and solvent molecules, and finally hydrogen bonding, if water or polar solvents are present, affecting the quantum dot stability. And finally, the blue pipe cleaners, which represent the emitted light, showcasing how quantum dots can release energy in the forms of visible photons, which can arrange in a vast variety of different colors. So this model helps just to visualize the fundamental structure and properties of a quantum dot, showing their size, shape, and atomic arrangement, along with their inter- and intramolecular forces, and how they influence its behavior. So, without further ado, let's move on to the physical and chemical properties of a quantum dot. One of the most important physical properties of quantum dots is their size-dependent emission. This means that the color of the light that they emit can be tuned simply by changing their size. The effect is similar to that of two different sized bells. When the larger one is struck, the result will be low energy sound waves, while the smaller one creates higher energy waves. When light excites a quantum dot, the larger the size of the dot, the lower the energy waves will be, resulting in redder light, while the smaller it is, the bluer light it will be. They also have high quantum yield, which means that they're extremely efficient at converting absorbed energy into emitted light. This makes them ideal for applications like display screens and imaging. Now, chemically, quantum dots are quite interesting. The reactivity depends on something called surface ligands, which are molecules attached to their outer layer. These ligands influence how quantum dots interact with different materials and how stable they are in various conditions. Now let's talk about safety. Because some quantum dots contain toxic heavy materials like cadmium, their production needs to be controlled carefully to prevent exposure. Manufacturing takes place in specialized environments to minimize risks to workers and surrounding environment. Handling quantum dots also requires even more safety measures. Protective gloves, masks, and fume hoods are recommended to reduce the risks of inhalation or skin contact, particularly in laboratory settings. Proper storage is also important. Quantum dots should be kept in dark, cool environments to prevent degradation and maintain their stability over time. Now, let's dive into the exciting electrical applications of quantum dots. Quantum dot displays, or QLEDs, is one of the most well-known uses of quantum dots. Traditional LED screens rely on white LEDs and color filters to produce an image, but this process wastes energy and results in less vibrant colors. QLED technology changes this by using blue LED backlights combined with a layer of quantum dot nanoparticles. These quantum dots convert blue light into pure red, green, and blue, which leads to richer colors, higher brightness, and better efficiency. A great example of this technology in action is Samsung's QLED TVs, which leverage quantum dots to enhance contrast and color, making the images more realistic. Quantum dots aren't just improving displays though, they're also revolutionizing green energy, more specifically solar panels. Quantum dots have the potential to revolutionize solar energy. Traditional solar panels can only absorb certain parts of the sunlight spectrum, which limits their efficiency, but quantum dots can be engineered to absorb a wider range of wavelengths. This is because they exhibit multi-exciton generation, where a single high-energy photon can produce multiple charge carriers, increasing efficiency. This makes quantum dot solar cells more efficient at harvesting sunlight. Now, this all may seem very groundbreaking, but that's because it is. And like any groundbreaking technology, quantum dots bring both positive and negative effects. Let's start with the benefits first. One of the biggest advantages of quantum dots is their role in advancing technology. As we mentioned before, QLED displays have completely changed consumer electronics, improving color accuracy, brightness, and energy efficiency in TVs, monitors, and smartphones. Beyond just consumer electronics though, quantum dots are making a difference in renewable energy. This leads to lower energy costs, wider access to clean energy, and a potential to reduce carbon emissions. However, despite all these benefits, quantum dots also pose significant environmental and health concerns. Many quantum dots contain heavy materials like cadmium and zinc, which are toxic and can leach into the environment if not properly disposed of. Contaminated water and soil can harm ecosystems, wildlife, and even human health. As quantum dot-based electronics become more common, improper disposal can also contribute to e-waste pollution. The environment is really one of the biggest concerns of quantum dots. While quantum dots bring technological advancement, their production, use, and disposal pose significant environmental challenges. The production of quantum dots involves high-energy processes that can contribute to carbon emissions, air pollution, and the contamination of land and water with toxic heavy materials like cadmium and zinc. Therefore, responsible manufacturing, use, and disposal are essential to mitigate the ecological impact of quantum dots. But it's not just the environment. Human health is also at risk. Workers in manufacturing environments may face short-term issues like respiratory irritation and long-term effects such as kidney damage or cancer. As electronic devices containing quantum dots degrade over time, the release of these toxic materials can lead to skin irritation, neurological damage, and organ dysfunction. But enough with the negative. Let's get to some more positive information. Current research on quantum dots in Canada is advancing in various fields, with institutions like the National Research Council of Canada and McGill University making significant strides. The NCR has been developing quantum dot nanoparticles since the mid-1990s and has successfully demonstrated quantum lasers, which could benefit high-speed data communications. McGill's Kabahatchi research group is focused on the synthesis and characterization of quantum dots, delving into their properties and potential uses in multiple applications. With all of these strides, the future is very positive. The future screens with quantum dots will be very small, light, and cheap, with the tunable quantum dots being able to generate saturated color in every screen pixel. Quantum dots will also be able to be deposited on materials, allowing for things like heads-up displays on glass and rollable and flexible screens. The future is bright, or should I say, the future is quantum. Before we wrap this up, we have to talk about green chemistry and green engineering. In terms of green chemistry, researchers are working on new synthesis methods that replace toxic chemidium-based quantum dots with non-toxic alternatives, like silicon quantum dots, and are exploring water-based synthesis to minimize the use of harmful solvents. From a green engineering perspective, quantum dots contribute to waste minimization and longevity. Quantum dot enhanced displays tend to last longer than conventional screens, which helps to reduce electronic waste, while their improved efficiency reduces their overall material usage. Additionally, emerging silicon-based quantum dots minimize resilience on toxic heavy materials, and future research into biodegradable nanoparticles is aiming to create more sustainable quantum dots. Future improvements include the creation of heavy metal-free alternatives such as silicon or carbon-based quantum dots, advancements in green synthesis methods to eliminate hazardous chemicals, and the creation of recyclable quantum dots to facilitate material recovery at the end of their life cycle. In my opinion, quantum dots have incredible potential to transform a lot of industries, especially in electronics and renewable energy. The fact that they can enhance display quality and energy efficiency is already a huge win, and their ability to improve solar energy capture could play a big role in the future of sustainable tech. That said, I do think we need to approach their development cautiously. The concerns about toxicity and environmental impact of traditional quantum dot materials are definitely something that cannot be ignored. That said, research into chemidium-free quantum dots and greener manufacturing methods follows green chemistry's principles by reducing hazardous wastes and improving sustainability. Their potential to cut energy use in electronics and boost solar power efficiency also aligns with green engineering by promoting resource efficiency. So while environmental risks exist, ongoing advancements in safer alternatives really do show a clear path forward. So overall, personally, in my opinion, I would say the societal benefits of quantum dots far outweigh their drawbacks as innovation continues to make them safer and more sustainable. I'm optimistic about the research being done to create safer and more sustainable alternatives, and I think the future of quantum dots will balance innovation and responsibility. That said, the future of quantum dots is truly bright and revolutionary for many, many industries. Thank you for watching. The end.